Hi, everybody. Welcome back to my YouTube channel, Theoretical Physics with Mark Weitzman. Today I want to continue with group theory in physics, and we'll go to we'll continue with special symmetry functions. So this is group theory in physics. And this is Schensted, Part 2, Chapter 1, Frobenius Algebra. This is video 4 on special symmetry functions. Now, before we get to the special symmetry functions, I want to just add something to the last video that we did on projection operators. Video 3 was on projection operators. And I just want to show you how just a simple calculation for the dihedral group. Remember the symmetries of a triangle. Symmetries of an equilateral triangle. And which Schensted uses the notation GB. I'm sorry. She says lowercase b. GB. And so let's use the formula. The formula for the projection operators, and you can see the representations for this thing is on Schensted page 27, my notes page 17, my notes on Schensted's book. So we're going to use the formula that we had in last lecture. That's going to be the sum from j equal 1 to n. In this case, n is 6. Gamma k. Aj is the group element. Star c prime. It's a little easier to use. This is for unitary reps. And the three irreducible reps shown in the book are unitary. So we can use this formula. So I just want to show you very quickly not that yet. Let's see, page 17. So this is the group E, C, C bar. These are identity, rotation, counterclockwise rotation, reflection on one axis, on one median, reflection on another median, reflection on another median. These are the representations. This is the trivial one-dimensional representation where every group element is assigned 1. This is the other one-dimensional irreducible representation where the reflections are assigned -1. And then gamma 3 is the two-dimensional irreducible representations. So for the For the first one-dimensional representation, we'll call that 1. It only has one matrix element because it's one-dimensional. And since all the numbers are 1, it's just the sum of all the group elements. E plus C bar plus sigma 1 plus sigma 2 plus sigma 3. The second irreducible representation also has only one matrix element, and it's again the sum of the group elements, but now since the reflections have a minus sign associated with them, we subtract them. So doing that, we get rho 1, 1 equal E plus C bar plus sigma 1 plus sigma 2 plus sigma 3. Rho 2, 1, 1 equal E plus C bar minus sigma 1 minus sigma 2 minus sigma 3. Okay. Now we have the two-dimensional representation. So this is, we labeled by 3 because this is the third irreducible representation. It's two-dimensional. We're going to have four projection operators to calculate. I'm going to show you the answer here in a second. Let me just go back. But the way you do it, again, you go to the representation. Here it's gamma 3. And you apply that formula where you take the matrix element. Like if I want 1, 1, if I want the 1, 1, I just look at the 1, 1 of all these group elements. So it's going to be 1, 1 times the identity. And then it's going to be minus 1/2 times C, minus 1/2 times C bar, minus 1 times sigma 1, plus 1/2 sigma 2, plus 1/2 sigma 3. So we get rho 3, 1, 1 is equal to E minus 1/2 C minus 1/2 C bar minus sigma 1 plus 1/2 sigma 2 minus, plus 1/2 sigma 3. And I'm going to put a little bracket around here. These are what's called partner pairs, because these will be associated with special symmetry functions that are in a column that all transform into each other. I don't want to. The other matrix elements are done the same way. Instead of taking the 1, 1 element of all the group operators on that page, you take the 2, 1 element. And I'm just going to write down the answers here. I have the square root of 3 over 2 minus C plus C bar minus sigma 2 plus sigma 3. And then the other ones, they're a little more complicated because you get these square root of 3 over 2 factors. C minus C bar minus sigma 2 plus sigma 3. And then this becomes E minus 1/2 C minus 1/2 C bar plus sigma 1 minus 1/2 sigma 2 minus 1/2 sigma 3. Okay, so that's good. So these are the projection operators for the three irreducible representation. This is the first irreducible representation. Remember the second irreducible representation, they only have one matrix element. And then the third irreducible matrix elements, we got four projection operators, and we label them by these matrix elements. So the projection operators are always a complete independent set of You could call them vectors. Remember, these are abstract vectors. Somebody made some comments, sort of ridiculous comments, trolling some of my recent videos, but there's two types of vectors in physics. The first vector is sort of what you learn in first year physics. You could think of it as an arrow and a magnitude. But that's not enough, because it also has to transform like a vector is supposed to transform. Spinors also have direction and magnitude, but they don't transform like vectors, so they're not vectors. The second use of vectors that we make in physics, especially as we get into advanced physics, is they're just elements of an abstract vector space. We call the abstract vector space a vector space. The elements of that vector space are called vectors. So you need to separate this thing. In this course, when I say vectors, most of the time I mean it's some element in an abstract vector space. So we have a complete independent set of vectors. We could call them basis elements, whatever you want to call them, for the regular algebra, for the group algebra. Sorry. So that's why we use the projection operators, and it's nice that they're always a complete and independent set, but they're hard to visualize. You know, I'm not sure exactly what this means, That's why often we use what are called functions, symmetry functions, to try to visualize sort of what's going on. And so if we apply a projection operators, we can apply projection operators to functions, usually complex, but not always, sometimes just real. And then we can sort of get a better idea of what's going on. So we define FKCC prime is defined to be rho K CC prime applied to F, where C equals 1, 2, dot, 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 lambda K, and C prime is fixed. So we'll get lambda K independent functions. F is some complex function of some maybe coordinates or whatever. We'll get into that in a second. Now, these correspond. If you look at our proof, if you go back to our proof in the previous video, let me bring that up a second. So this was our previous video. I want to look at my notes. The iPad Pro notes. Okay, this should do it. So we look at these notes. We went through this proof. We applied group operators to the projection operators, and then you used a rearrangement lemma, and we showed that they transform. If every one of these lines you stick F at the end, everything is still valid. So we're going to get the same thing except applied to symmetry functions. And let me go back here now. So what we can show using the same proof that we did there is that FKCC prime, if we apply a group operator to them, that's like, that's the symmetry. We're applying a symmetry group operator. That's going to be equal to the sum over C double prime, gamma K, AH. Remember, C prime, this just goes along for the ride. It's a slang term. If you're not English, you might not understand it. But anyway, C double prime C, FC, FC double prime C prime K. So we're summing on these. These are the summation indices, the C, and you can see the C prime goes along. And again, C equal 1, comma 2, comma dot 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 lambda K. And this is the way partner are supposed to transform. So that's good. The only problem is that these set of functions, FKCC prime, need not be independent. Here I'm talking mostly across that fixed index, like different values of C prime, need not be independent or non-vanishing. And usually, okay, this happens when the original function f has already some symmetry with respect to the group. So as a with respect to the group G. Okay. So when this happens, we're not going to get a full set. We're not going to get an independent set. We could get a completely vanishing set. I'm not sure you can get a completely vanishing set. For some C prime, they probably won't be vanishing. But to give you an example of this, if we consider the two-element group, this is a very easy example. The two-element group, that's sort of like, and if we start with a symmetric function, the projection operators will project it to the symmetric functions. We'll never get, we will not get an anti-symmetric function. We will just get 0. Because remember if we start with F, the two-dimensional, two irreducible representations, the group elements are E, and let's say inversion, and the reps are 1 and 1, and 1 and -1. So if we apply the projection operators, we're going to get like EF plus IF. Okay. So that's going to equal to, since it's a symmetric function, that's just going to be F plus F is equal to 2F. We could normalize it. But when we apply the anti-symmetric representation, we're going to get EF minus IF, which is equal to F minus F, which is equal to 0. We're never going to get an anti-symmetric function. Likewise, if we start with an anti-symmetric function, we'll never get anything in the symmetric function. So that just illustrates what happens when you start with a function that has the special symmetry. And now I'll show images which illustrate this, images for the dihedral group, GB, which illustrate this. This is on pages 80 of and page 42 of my notes. So let's go look at that to see some further examples. Lost. Okay. Page 42. I'll get it in a second. Okay. So these are my notes on construction of special symmetry functions. These are the formulas that I showed earlier. When you apply all the projection operators to function f, we get a square array, lambda k times lambda k of functions. And functions in the same column are partner functions. They transform among themselves. But some of these columns could be duplicates. They're not necessarily all independent. Some of them could be all zeros. So you have to start with a function that doesn't have any special symmetry. Now let's sort of give an example. Schensted gives this example in the book. She starts with a function. It's only the black dot represents everywhere outside the black dot, the function is 0, but inside the black dot, which is a half semicircle on the top of the triangle, it's plus 1. Then when we apply the group operators to this function, you can see what happens, and she shows it, clockwise rotation, counterclockwise rotation, reflection, and then reflection about that median, and reflection about that median. Now when you apply the projection operators to it, you can see, if you remember our previous thing where the trivial representation, the first irreducible representation, which assigned 1 to every group element, you're just going to add up all these things, and the first diagram and the second diagram will add up to a circle, so everything's just going to be a circle around that point. So that's easily understood. Same thing with the second representation, except now it's going to be minus with respect to the reflections. Remember, the rotations don't flip it over, but the sigmas do, and we're going to get minus. So now we get, it's only non-zero in a circle, but it's plus 1 on one side of the circle and minus 1 on the other side of the circle. So that's also easy to understand. Now, for the irreducible representation, it's not as easy to see, but this is the result. We get these kind of symmetry functions. This is one where it's all on the circles on the thing with the plus minus and the plus minus. It's not quite the same thing. You might think that this is the same as F2 here, but it's not. Because F2 has 1 minus 1. That's the same. But these two are opposite. These two are flipped, and these two over here are flipped compared to there. So it's a different symmetry function. And then we get its partner pair, we get this symmetry function. Because if you imagine subtracting, I think if if you add the negative of this, well, not quite the negative of it, but if you add like, I think this plus this, anyway, this is another symmetry function in that partner pair. And it's got a square root of 3 over 2 multiplier. And then the second set of partner functions, you would get this, these two things here. And when we do vibrations in the next chapter in Schensted's book, some of these things will become more relevant. But let's just show what happens if we start with a special function that has symmetry to start with under the group. So here we have this f is just this, and this is symmetric under the reflection about the y-axis. So it already has a symmetry with respect to the group. Same thing here, if we counterclockwise rotate, we get that, but this was also symmetric under the reflection through this median, and this is symmetric with respect to that median. Now when we take the partner pairs, we're okay on the over here. It's not quite the same, but you know, I'm sorry, F11 is the same. This is the same as the one-dimensional representation, but the two-dimensional representation, I'm sorry, the second irreducible one-dimensional representation is absent. It's all 0. And in the two-dimensional representation, one partner pair is all 0, and the other partner pair is this. So this just shows how you need to be careful when you choose functions. Try and general lesson, start with a general function f which does not have any kind of symmetry with respect to the group. If you do that, then you'll get all the relevant symmetry functions. So thank you for watching, and we'll continue with more theory, introduce things like simple matrix algebras in the next video. I'll see you next time. Bye-bye.